Hi everyone. I'm going to do what is called a ladder problem. It's a pretty common problem on the AP, and essentially we're using the idea of equilibrium to solve it. So ideally is that we have forces acting on this system, but we have too many unknowns, so we're going to use torque as a way to eliminate one of the unknown forces and solve for the other features, whatever the question's asking for. So I have this on my slides, and this is just an example of how to apply torque in a static situation. So let's go ahead and take a look at it. So we have this ladder. Just going to go ahead and do, oops, there we go. So you can see we have this ladder right here, and it's leaning up against the wall, and the wall is frictionless. And then it says that this person starts to walk up this ladder, and then it just begins to slip. So the question is, what is the coefficient of static friction on the ground? Okay. So first and foremost, as always, we always find a free body diagram. And since we're really interested about torque, we have to be careful about the force locations. We have to be very particular because we need to know and model correctly where the forces act on the system. So I usually do the same thing anytime I solve these problems. I start off with the center of mass, the weight of the object. Now since this is a uniform object, it will happen right at the center here, so there we go. So this is the center of mass, which we concentrate all of the weight. So I'm looking for the weight. So the ladder weighs 400 newtons. Now in this specific problem, they actually give us the full weight. It's not mass, it's the weight. And because of that, I'm just going to use that number later for force, because we don't need to multiply it by g. So that's actually pretty cool. The next thing is this person has mass, therefore weight, and it's going to push down on this ladder. And this person has an 874 Newton weight, and I'm getting this from the problem right here too. So this person's 874, this is 400. And those are, I would say, the most, I use the word obvious, but it's not obvious. This is the problem, the information you get from the problem directly. But really, there's a couple other things that's happening in this question that's not so, I'll say the word obvious, but not as directly given to you. So first, this ladder is going to feel a force right from the wall right here. Now the wall can only push outward. In fact, actually, even though I have it as F wall, this is actually normal force, because normal force can only push outward. So this ladder is going to be pushed outward at this point by the wall. So I'm going to label that there as FW. Now remember, we're looking in the perspective of the ladder, so the ladder is going to feel push from the wall this way. We're not modeling the push that the ladder pushes on the wall. This is what the wall does on the ladder. So that's why it says perfectly to the right. Now, of course, my drawing's not perfect, but I think if you, visualize this, you can see that's the case. The other point of location is here. And two things. Same thing. We have a force from the floor down here as a normal force. So I'm just going to write the word ground. But quite honestly, this is also a normal force. And this is too, but of course they're different walls, so they're different forces. So this is a normal force down here, and technically it's a normal force. But the ground will push up. And the reason why it pushes up, because the ground can only push out from the surface. And in this case, it's going to be the floor. Next, we have friction at the bottom here, because it says there's friction at the bottom with the clue of coefficient of friction. So the question is, which way does friction act? Well, if I were thinking about this problem, and this was leaning up against here, the ladder would actually slide this way if you think about it, because these things are pushing it down, causing this side to rotate down, which means this would kick out. So, to stop that, friction must oppose that direction. So, in our ladder problems, unless otherwise specified, the friction is always going to go inward toward the wall, because that's the direction at which friction will act to stop that. So there you have it. We have our four forces. So it's always good to just check to see if you can find it through net force, but I'm going to make a bold assumption here and say that we're going to have too many unknowns. In fact, force, friction, normal, and force wall. But let's still model it. So let's find the net forces in the x and set them equal to 0, and then in the y and set them equal to 0. Because, hey, if we don't have to do torque, then we can save us some trouble here, but like I said, I'm going to assume that this is not the case. So here's our horizontal forces is the wall and friction, right? So the wall is positive because I have it modeled to the right, minus friction because I have it modeled to the left, equals to 0. Now, of course, I don't know either of these, but the good news is, if I were to just rewrite this, is if I know the value of friction, I know the value of the force on the wall. But of course, that's not what the question's asking. In fact, it's asking for coefficient of friction at the bottom here. So let's go ahead and do this one. Force net in the y. I want to set that equal to 0. So here's the modeling of the equation. You notice here, I have the weight of this person as 874 newtons down. So I'll have that as negative. I'll also include the negative 400 down, because that's down, plus the force normal of the ground, and that's going to equal to 0. Just like that. And that is officially our case, because there's no other components here. So what we find is actually we can find the normal force because we have that value right here. Now the normal force is going to equal to the sum of these forces like that, which is good. And then, yeah, so here we go. So if I add those two together, I could actually find the normal force. If I move this over, the normal force is the sum of those two forces. So 874 plus 400 gives me 1,274 newtons of force upward, like that. Cool. Almost, because remember, force friction is going to be force normal times mu. So notice if I want to find coefficient of friction for this problem, I still need a force friction. And as you can see, force wall and force friction, I can't really get any information out of this. So that's when we go to torque. So if I choose this as my pivot point, I can eliminate the force of the wall, the unknown that's happening here, and then analyze this in terms of torques. So we say that the net torque of the system must equal to 0 because we have to stay in equilibrium here. Or like I like to do in class, the torques clockwise have to equal the torques counterclockwise. So I have them placed where they need to go. Let's find their direction. So if I go around the pivot point here with this force, I'm going clockwise, so this would be a clockwise force. Same thing here, this would also be a clockwise force. And then I have this also going clockwise. But this one is going counterclockwise because we're going up against this direction. Okay, so there's all our clockwise and counterclockwise forces, and now we can model them with the correct measurements. So let's go with our clockwise forces. Now I need the distance from here to here. That's going to be my R for this force. Now this is 7.8 meters, and this is what it should be, by the way. 7.8 meters. Which means, and this whole thing is 12 meters. So I can get this little piece right here, which I'll just call R. It's going to be the total length minus that little piece there. Oops. So minus 7.8. This is 4.2. So my first torque comes from this one. Now as a reminder, torque is force times R times sine of the angle. So here's where it gets fun, right? So notice that this does not make a right angle to our system. So let me let me take this out of the problem. So if you notice right now that I have this force here as 874 newtons, I have this as 4.2 meters, like that. So the question is, what is this angle? Essentially, that is what I need to figure out here. So let's see what we have to figure this out. Okay, so what I do know about this system is the following. I do know that this is 51 degrees here. I do know that this total is 12 meters here, like this. So essentially, there's a couple ways I can do this. Now, the angle between here and here, right? So if you look at this, if I cut this here, like that, so that this is a right angle. We already knew that this is bigger than 90 degrees right here. So the question is, what is this angle right here? Now, if this is 51, this angle right here is 39 degrees, which means that this angle then is 51 here, like that. So I'm doing a little angle analysis. So it turns out that it shouldn't matter which one I use, because the most important thing is I want to select out the component of the force that goes perpendicular. So I want this component of our force right here, because this is this makes a perpendicular to the whole system, like that. So with that said, I want to use the 39 here, because if I do 39 sine of the angle, it gives me this part, which is the correct representation. If I did this and did sine of the 51, let me just show you. The angle, this is the opposite part. And notice that this, if sine 51 is this red angle or arrow here, that goes along the force, and that will not cause it to rotate. So, moral of the story is the answer is I want this to be 39 degrees from that, just based on my analysis. So, doesn't matter. I mean, you could also do it as, 39 plus 90. That's fine if that's more comfortable with you. 39 plus 90 would be 129. Whether you use 129 or 39, this is the angle you want to use to solve this. So coming back to our lovely problem right here, where it's now different, it's set up like this. So torque, actually, hold on one second, let me just go down. I'm just going to go over here. So torque clockwise equals torque counterclockwise, like that. My first one, torque is force, so 874 times distance, 4.2 meters from the pivot, times sine. And like I said, you can use either. I'm just going to use 39 just because I want to use it. Times 39 like this. Okay. Plus. Our next one is right here, the 400. Now this is halfway from here to here, because we're at the center of mass, so that's 6 meters away, like this. Now this makes the same angle as this one down here, so I'm going to use the same analysis since it goes straight down. So it's going to look like this. It's going to be 400 newtons times 6 meters, because that's the distance from the pivot, times sine 39 degrees. There you go. Alrighty. Now, the last clockwise force, so I just did the clockwise, here's the other clockwise force. So this now makes an angle of 51 degrees, right? So that's this bottom one right here. So I'm just going to draw. So the force is doing this. So I want the component of the force that makes the right angle, right? I want this part. So if I use 51 sine, then that's okay. So, plus force friction, which is actually what we're solving for, times where it is, it's 12 meters away, because that's the length of the ladder, times sine of 51 degrees. Now I'm using sine 51 because when I do, and I use this triangle, oh, hold on, careful, let me make sure, this is why I'm talking about it. Make sure that it is the triangle I want to use. There we go. Sorry. 51 degrees. I made this into a triangle like this. This would be 51. Okay? And then this would be my components. So neither of these go perpendicular. Great. Because these are both at angles, so that wouldn't contribute. And I'm sorry, hold on. My force is going this way, like this. So that's my force of friction. Oh, I see what I did. Okay, so I made the right angle here. And if I use 51, this would be that angle. And then the component of the force that is this part, because that's force friction, would be, it's still the sine component. Okay, that still works. So what I'm doing here is, I'm just double checking. So remember, this is the force right here, and the R is this right here, like that. So the angle between R and F, what I did here is the 51 degrees does accurately model the perpendicular component that we need for this. So that works. So 51 degrees. Perfect. Okay. That's all the torques of clockwise. Now we got to do the counterclockwise force, which is this one, which is the force normal, right? So we got that from the previous problem, actually. So that is the 1274. Perfect. 1274 newtons times its distance away, which is 12 meters, times the angle. So notice that the angle that these two make, if this is 50 degrees, then the angle right here is going to be the 39 right here. And if I do that, the 39 gives us the component of the force, so sine 39, like that. Okay, so the hardest part about these is these are no longer at a right angle, so we have to figure out the part of the force that gives the right angle. Or in other words, find the angle that gives the right angle component. So this is, of course, the difficult part about solving these problems, is figuring out which angle to use. So here it is in all its glory. I'm going to go ahead and simplify all these, make sure I'm in degree mode, sorry. So 874 times sine 874 times 4.2 times sine 39. This is in torque Newton meters, plus, let's do the next section, 400 times 6 times sine 39 gives me 1510.37 plus 12 times sine 51. Force friction, sorry, that's not supposed to be scribbled out, times 9.33. This is in meters. And then we'll do this whole side. 1274 times 12 times sine 39. Nine 621.05 Newton meters. Okay, I'm going to go ahead and finish this problem by getting the F by itself. So I'm going to combine the 2,300.11 plus 1510.37, and then I'm going to subtract E. Okay, that looks good. Subtract that from the 921. I'm just doing out the algebra now. I guess I could show you my step-by-step algebra. So here we go. I just simplified this and I get 3,820.48 plus this stuff equals this. Okay, so I subtract that on both sides, and then I get this. There we go, and divide both sides by 9.33. I get a force of friction 621.71 newtons, and almost. So that's the value of our friction. But force of friction is equal to force normal times mu. So force of friction 621.71 newtons. And then the force of the normal force is the 1274. We got that earlier. So let's go ahead and solve for mu, which is going to be 621.71 newtons divided by 1274 newtons. 0.4, I'm going to round 9, is the coefficient of friction, which looks good. Okay, and that would be the coefficient of friction. So, hardest part now about this problem is recognizing the force of friction down here is actually inward, that the ground pushes up, that the wall pushes straight out. And in fact, we figured out the wall's force because we figured out the force of friction. So the force of friction, what did we get, just to be complete, was 621.7. So 621.7 newtons. So that's the force of the wall, so we were able to figure out that now. But the hardest part is figuring out, now that these are no longer at right angles, which angle to use. You always want to take out the angle that selects out the component of the force that makes a perpendicular angle. So notice you had a couple options here, and then looking at these in that way helps you set up the problem. So I know that's what I did here was probably a little crazy to see the first time. I recommend you try it on your own and try to figure it out. I also recommend that you watch it again to see if you can pick it out. And if not, definitely come see me after school or another time to kind of think about what I did here, because it's not, if you notice, I didn't just apply the equation. I had to figure out which force, what's the direction that causes the perpendicular motion, which causes the rotation, which is not just a simple plug and chug of the equation. So if you have questions on that, let me know. If not, welcome to the ladder problem, and I hope you enjoyed.